opportunity for the young generation.
Thank you very much for the kind introduction, and thank you for having me. It's a great pleasure and honor to give this talk. So I hear that you are learning a lot of machine learning right this week. And I'll try to cover some topics and provide a little bit of context maybe. So my talk is gonna start with some overview, what we do in particle physics with machine learning, and as you heard, I'm a relatively late convert given my professional career. Yeah, and then I'll show you 3 different applications to anomaly detection, event generation, and formula extraction. But let's just start, with something that, no matter what we do in particle physics, we shouldn't forget that we're trying to understand something that's very, very fundamental. Is questions like, what's dark matter? Why is there more matter than antimatter in the universe? Where does the Higgs field come from? I mean, our experimentalists, I shouldn't say our experimentalists discovered the Higgs boson, but really we have no idea where this field is coming from and what its dynamic origin is. So these are the physics questions we're trying to answer, and we need to keep this in mind now, no matter how technical we become, and we will usually become very technical, and that was that way before machine learning, and it's certainly that way with machine learning. So these are the questions, and then if you think what kind of defines what makes LHC physics what it is that we have these fundamental questions, and then we try to answer them with a huge data set, one of the biggest data sets, maybe the biggest scientific data set in the world. And the opportunity that we have that most other fields don't have is that we can use first principle, quantum field theory based precision simulations to understand that data set. And on the experimental side, as well as on the theory side, we benefit from a complete or an extremely high level of uncertainty control. So we can make very precise statements. And this is, by the way, a challenge whenever we apply machine learning, as you'll see, because machine learning is not actually a field that typically benefits from uncertainty control. Before we have about the future, we should also remind ourselves that in particle physics, we have a very successful past. Not only at LHC, but even before, people measure stuff, they measure couplings, they measure masses, essentially by counting events. I mean, all we do is we count events. And then we do analyses, and there's this pheno field, phenomenology, where theorists think about what would be a cool analysis, and then you try to explain this to our experimental friends, and they improve it, and then they do these analyses. And our big discoveries, including the Higgs boson, but also before, tend to be driven by our understanding of the underlying physics models, which guides us to these these classical motivation questions I mentioned before, dark matter. So this is model-driven research. The problem with that is that at the LHC, everybody had great hopes, including me. You heard I'm an old SUSY guy, to discover new physics, and well, we didn't until now. So that's the problem that we have to deal with. As I said, one of the great tools that we have to understand LHC data is first principle simulations, which in particle physics, by the way, different from many other fields, are done by theorists. So we start with the Lagrangian and we calculate some scattering rate using quantum field theory, and when we simulate these collisions, and then we ask our experimentalist friends, and they tell us how to simulate a detector, and collisions in a virtual world, and that virtual world is described by Lagrangian. So that is I'm currently teaching first-year students. We actually write down the Lagrangian, and then that defines our virtual world, and then we generate 100 million LHC events or something like that, right? So this is I think why I like LHC physics, because we can do that. This picture is a famous picture from the Sherpa collaboration on how they envision an LHC event. And then we search for physics beyond the standard model, essentially by comparing simulations and data. That's what I think we should do. And we should analyze data as systematically as possible, because you don't want to miss anything interesting, right? I mean, nobody wants to create data and then miss something. And if we analyze data systematically, we can actually say, okay, but we look at the data and then we just infer what the underlying theory is, given that we can actually simulate in a virtual world. I mean, that would be like we just looked which similar data set agrees best with data, and then we like check what like range in that was, and that is our nature, right? That could be a standard model. That's not going to make me so happy personally, but it might well happen, right? Or it's some physics beyond the standard model, which is going to make us, all of us, much happier. No matter if it's BSM physics or not, you know, and that's important. At the end of that, like exercise, we can say we totally understand science. It's more important to say we understand everything than to try and, like, you know, guess what might be in there and then get disappointed because your favorite model had not been discovered. Yeah. And then, like we talk a little bit about later, like, you know, when you do that, you also want to publish useful results at some point. You want to publish stuff in a way that people can use it. And the questions that I just, like, you know, raised are essentially a bunch of data science questions, if you think about it. And I mean, like, you know, if you can explain what I just did to like an average data scientist who might not even have a physics background, they understand that. They understand what simulation-based inference is. They understand what simulations are, and so on and so forth. Well, you might have to explain to them what the Lagrangian is, but, like, you know. Okay, so that's just, like, you know, this is my favorite line here. Like, you know, it tends to not make all my experimentalist friends happy, but, like, you know, so how are physics questions related to data science questions? Like, for instance, the question, how do I, like, you know, in LHC physics, how do I trigger such that, like, you know, my data stream of Atlas comes down from, like, you know, 3 petabyte a second to the 300 megabyte a second that we can write on tape, right? And you can say, oh, well, yes, Atlas trigger, they're really great at that. But you know what? That's just data compression. And people who know how to do this usually, like, are employed by companies like Netflix. I mean, Netflix, like, you know, streaming TV is a masterpiece of data compression, if you think about it, right? How do I analyze events with 4 vectors? Like, you know 4 vectors, energy, momentum. How do I analyze them? Well, I don't know, maybe has told you about that, but one of the kind of networks is graph neural networks, and graph neural networks is what we know from car cameras. Like, you know, well, people, like, you know, cars, like, trying to identify if there's a person crossing the road. This is a graph neural network, and this is exactly what we do. How do I incorporate symmetries? I can, like, you know, give you a very brief example later. We actually learned this from Google. It's called contrastive learning, how to implement symmetries in training data and understand them. And a really crucial question experimentally, how do I combine tracker and colorimeter? Because these two, like, you know, parts of the data analysis chain have very different resolution. And how do I combine images with very different resolution? Well, gaming has exactly the same problem, right? I mean, you need some of the picture that, like, you're working with very high resolution, but you don't have the, like, bandwidth to make everything high resolution. So you use a tool that's called super resolution neural networks. How do you remove pileup? Well, oh, that's easy. Like, pileup, like, you know, we think it's a very big problem, but, like, everybody in data science knows it as denoising. How to look for BSM physics. Now, that's interesting because that actually brought me, like, you know, like, one of the things that Ramon was to talk about this. One of the things that brought me to machine learning was, like, you know, sitting in, I still remember, in a coffee place with a friend of mine who works for SAP. That's Europe's biggest software maker. He's just outside Heidelberg. Based just outside Heidelberg. He's also a trombone player. And so we discussed about, like, you know, autoencoders and anomaly searches. And then we found that tools to, like, search for anomalies in business computer networks just analyze, like, you know, network traffic. And they see, like, you know, if something goes wrong, if the computer network gets hacked, network traffic patterns change, you switch off the computer, right? For us, the network, the nodes of those networks in jets are just jet constituents, and then they have, like, some correlation. And if something is funny, well, that's the BSM jet. It could be dark matter, just semi-visible jets. So, like, we want to analyze in more detail. It's really exactly the same question. How do we analyze data? I already talked about this. Is, like, you know, simulation-based inference. The only question, like, you know, from that list, like, you know, the only point where you're going to have a hard time convincing, like, you know, a data scientist to help you in LHC physics is when it comes to the topic of uncertainties, because uncertainties is something where, like, you know, LHC physics, like, you know, really is, you know, heading like in the movement. Now, I know you learned a lot about machine learning, so like, already, so like, this is my one-line introductory slide. Essentially to me, a neural network is a fit. Like, you can ask someone about this. So you know the function and you want to approximate it with f theta. And it's not just a simple parameterization, it's a very like high-dimensional parameterization, but it's just still a parameterization. And what you do is you how to construct that, that is the trick. You minimize a loss function. And everybody who's ever done a fit knows that, because I mean, in the fit, we minimize chi-squared. Like, this is not a new idea. People have had that. So if I minimize our equivalent thing to chi-squared, or if you ask me, like any loss function should really be like something like a likelihood. And then for LHC applications, I'm going to talk about this. There's like, I can see at least 4, there's more, but at least 4 kind of networks that we apply. Like, one is simple regression, so learning a function. Then it's classification, to which we learn a function that is the probability of something being something else, like, probability of a jet being coming from a top quark, for instance. The next network is generation, where like, our function maps random numbers from which we can sample onto like some phase-based configurations. And then the most recent addition to that is a conditional generation, where you do the same generation, where you assume like a certain other thing, like as an aspect of the data. We'll talk about this later, but this is really like regression, classification, and generation are the kind of networks you're using. And these 3 networks are transform numerical science. And what's important to remember is LHC physics has always been a numerical field, very numerics oriented since I started. Like, I've never done anything on with pen and paper. So this is a numerical field, and any numerical field like benefits from these kind of developments. So let me just like run like through a bunch of like applications of machine learning of the last couple of years, so you get an idea what we're doing. And then, as I said, I'm going to focus on 3 that I like currently at this point in time particularly. I think the credit for like making machine learning at LHC like a big successful field goes to the subject community. So the people who used to meet for the Boost conference. And the simple question is like, how can I identify like, what part on a jet might have come from? And this is a very, very, very old story. Like, B tagging, bottom quark tagging has been like, around forever and ever. And that has always been a multivariate problem for us to solve. And so like using machine learning or like, neural networks for that is just a very natural step. What's important here is, if you want to look at some point, if you have some time, you want to look at this article for top tagging using machine learning, is that machine learning like beats the classical methods by like a huge margin. It's not even like close. The other thing is, if you look into this paper, at some point you find that that the different methods how to use machine learning, the different architectures, like image inspired, like language inspired, like physics inspired. All of these methods actually do comparably similarly. So like, there is no wrong or right way of representing, LHC data and feeding it to a network. You just like, have to get it right. But like, there's many ways to get it right. And you can succeed many ways. So that's fun, because that means it's not just one group that wins. It's like, we can try lots of different things. Something related is, I don't know if this combination of tracking and calorimeter information into particle flow objects, we call them. This is what experimentalists do for as the kind of their first analysis step when they look at jets. And this is again a beautiful machine learning problem. I like that paper. That is a work like by Alan Gross, Maru Mikado and friends, because they employ like everything you can think of in machine learning, including super resolution. Everything we love is just in there, and it's way beyond concepts, and this is actually a ready tool. People can use it. Like, these kind of things like taggers, particle flow, this is all ready to be used. My favorite, one of my favorite topics has always been anomaly search, looking for a physics beyond the standard model. If you don't know what you're looking for, I'm going to talk about that later. You cannot ever talk about machine learning at the LHC without at least mentioning NMPDF. So neural network pattern densities. So whenever somebody says, we would never use actually neural networks for like LHC physics, You ask them, look, do you guys know what NNPDF stands for? Because, you know, NNPDF is a neural network parton density. It's, how do I say that? It's so, it's been around so long that the original version was coded in Fortran, just to give you an idea. But I mean, this has been around forever. And Stefano Forte has been leading this group. I know Stefano also forever, and it's a little bit sad because, you know, Stefano, like, you know, worked on machine learning. I've watched him do this for like 20 years without following that path, and like only very recently then I have switched side to his side. So yeah, NNPDF is like the success story in LHC physics and machine learning for, like, I don't know, since essentially like for more than 10 years. Something I like is, of course, as a particle physicist, is understanding symmetries in data. And there's a million different symmetries in their data. Like, you know, we have like rotational symmetries of the detector. We have the rotational symmetries of jets. We have like gauge symmetries. We have Lorentz symmetries. Like, you know, the world exists of symmetries, right? When we teach particle physics, we introduce the concept of symmetries, at least now, at the end of the first semester. And then we never like drop that topic, like, you know, it goes right through, like, you know, the end of, like, you know, our master and graduate education. So learning symmetries is really important. And that's a nice paper. It's about a bunch of physicists like Veronica Sanz and friends. And it's nice because, you know, they look at pieces of art and they basically use neural networks that the same CNNs we use in particle physics to identify, like, you know, Z2 symmetries in Van Gogh's paintings and stuff. Like, you know, if you want to read it, it's great fun to read. Of course, like, you know, that's not exactly what we're doing. So if you want to incorporate like symmetries in jet, in physics, for instance, you know, there are symmetries like a rotational symmetry, or like, I mean, think of think of, like, you know, the quantum field theory and the fact that a soft gluon radiation cannot change the pattern of a hard quark. You think of that as a symmetry or an invariance as well, and just put all of this into, like, your network, to analyze jets. And, like, you know, the technical tool that you use for that is contrastive learning, CLR, and transformer networks. It's great fun to play with. I won't be able to talk about this today. Something that people are working on, Ramon is working on, like, you know, everybody's working on, is how to speed up event generation, Sherpa or MATGRAPH. We call it madness, MATGRAPH neural importance sampling, because for run 3 and run 4, so high-lumi run, the current version of MATGRAPH is just too slow. Not a whole lot too slow, but, like, you know, a factor of 10, 20 too slow. And the hope is that we can actually enhance the speed of these simulation tools, both actually event generation and detector simulation using machine learning. If you want to do this, there's a very interesting question to answer, and that is, think of, like, you know, what's inside of every, like, you know, machine, every event generator. There's transition amplitudes, matrix elements squared, right? Actually, it's matrix elements, helicity amplitudes, and then squared. And so you calculate them, and you do this at leading order with, like, you know, the old, like, you know, MATGRAPH algorithm, and it's super fast. And, like, you know, Sherpa has corresponding algorithms, also super fast. You do this to next to leading order at one loop, and it gets slower, painfully slow. If you have, like, you know, a 2 to 4 process, very painfully slow. Like, you know, if you have higher multiplicities, TT bar, and you want to calculate stuff off shell, extremely painfully slow. And then you do 2 loop, and then you die. And, like, you know, it is like, you know, it is super hard to calculate these amplitudes at high loop level every time analytically. So our hope is that we can speed up this kind of evaluation with neural networks. As a matter of fact, if you look inside the 2-loop calculations by people like Gudrun Heinrich, you will already find interpolation tools there, and you can use neural networks there because we know that neural networks beat any other interpolation tool in terms of precision. We know that from NNPDF, for instance. Okay, something, like, you know, that I like, especially, like, you know, and we talk about it later, is before we actually do this, like, you know, enhance our event generators, we need to somehow understand how, like, we can generate stuff in phase space. This is, by the way, like, this is Ramon's core expertise. Like, you know, this is, like, you know, he knows everything about that. So I will only touch on, like, one additional cool little tool, and then he'll explain the rest of that topic to you at the school. The same thing with unfolding. Unfolding has been around for a long time. Essentially, the question is, like, you know, can I look at a particle configuration at an event after detector, and like, infer what that event had to look like at pattern level or something like that. This is what we call an inverse problem, really, like, in a much broader audience, for a much broader audience, that would be an inverse problem. And LHC physics has its kind of inverse problem, and that is called unfolding. And I'll talk a little bit about that later. Something I won't be able to talk about, even though it's extremely cool, is if you look into formal physics, we have this like string landscape, or like, the swampland, or whatever, like, that structure is, where your like vacua set, and like, either they're inhabitable or not inhabitable, from a quantum field theory perspective. And so you need to find like, islands of life in the string landscape. And this is, I think, one of the coolest applications of reinforcement learning, to basically walk through, like, analyze this huge dimensional landscape and then find new islands, new structures where like we can exist because the theories are normally free or something like that. Yeah. So this is like, a really cool application. Reinforcement learning, like, AlphaGo, is not something that we have used a lot in particle physics. And the string landscape is one of my favorite topics there. And the last thing I'm going to talk about is, I'm a theorist, and of course I have to do numerics, but I don't want to just do numerics. So like, I want to work with formulas. Formulas are my language, right? I mean, we know, like, this is the basis of like, perturbative quantum field theory is, I mean, that you can write a simple formula that you understand, and you can look at it and you can understand everything about it. And then you can, like, work with it more and go to higher orders, and things become very complicated, but you have still understood the leading term. This is just Taylor series. And like, you can do the same thing with using machine learning. And this is like, what gives me great hope also in terms of interpretability, because we can actually go back, we can go not only from formulas to numerics by being more and more precise, but then we can also go back eventually. And I'll talk about this a very little bit. So that was just running through all the different topics. And now I'm going to pick 3 of them that I like especially. And 3 of them, which, like, my group, or our group in Heidelberg, has worked on, like, over the years. So the first one is really just, like, capturing, like, the spirit of the LHC as a discovery machine. So if you think about it, when we built colliders, hadron colliders, or the LHC, that most of the stuff that you will produce is just quarks and gluons jets, right? I mean, you produce quarks and gluons, the interaction is QCD, you produce jets. And you can put tons of them, like huge amounts of them. Actually, so many that, like, you can't even write them on tape, and nobody's interested in analyzing all of them. And also nobody could analyze all of them because there's way too many. So, like, all of our QCD we can't look at. And now the question is, how do we find, like, the tiny number of events which tell us something new about nature? Like, that could be, like, dark matter, it could be CP relation, it could be, like, for baryogenesis, it could be something totally unexpected, it could be a new particle, it could be like a heavy vector quark, it could be scalar lepton quarks, it could be, like, another gauge boson, it could be really all of these things. The only thing we know about them is that they have different structures from the standard QCD events, and that the numbers are very, very, very small. So now, as I said, if you look for, like, the machine learning tool that can do that for you, you end up with unsupervised classification, or the tool is autoencoders. So I've, like, from our first autoencoder, like, I've picked our little picture. So what the autoencoder does, it maps a typical LHC event essentially on itself, and it compresses it in the middle. And if you compress it in the middle, you force, that, like, so-called bottleneck layer to encode the structures that, like, really make your QCD jets a QCD jet. And then if you feed another jet, like a top jet, through that, it doesn't fit into this representation, and that gives you a bad reconstruction error. So, like, what comes out is very, very different from, like, what you put in. And that measure you use, or one of those measures, that measure you use to identify anomalous stuff. Now, when you do that, and we always do that, like with QCD and top jets, what you find is that if you want to train the network to reconstruct QCD jets, indeed, top jets are hard to describe. Why is that? Because in QCD jets, two jets never have the W mass. You know, they have a much smaller mass and it just doesn't fit. The W mass doesn't fit, the top mass doesn't fit, and so on and so forth. Problem is, though, if you do that, the same thing, and you train it on top jets, right? So on something that's relatively complex, then QCD jets fit right in there. Why? Because QCD jets have less structure than top jets, which means they just look like very, very simple top jets, right? They don't look different from top jets, just like simple top jets. So that's the problem when you want to run these autoencoders. You have to make it so you learn when you study them. You understand that, like, you know, at some point that they work like with compressibility. They like check how much you can compress your data. And who knows if my new physics is less compressible than QCD? Why should it be, right? If you take dark matter carries away stuff, like, you know. So if anything, like, you know, a jet that has dark matter particles in there has fewer constituents, which means it's less compressible, which more compressible than a QCD jet, has less information. So, like, you know, our autoencoder will just fail. So autoencoders are a great tool, but, like, you know, you can work with them. However, when you look at them, you immediately notice we have to work with them. You have to make them better because our standard setup doesn't work. Okay, so one of the things we try to do with the group here in Heidelberg, we try to understand the structures of this, like, bottleneck, the latent space. And you can do that. Everybody knows that, like, people are doing this by, like, you know, go from an autoencoder to a so-called variational autoencoder, just to induce, that just induces a structure in your latent space. Thing is, when you do that, when you do this, you do that study, you do this analysis of, like, QCD and top jets, you notice that you learn exactly nothing from it. Like, it doesn't make your regular autoencoder any better in any way. It's just, like, you know, it doesn't help. And I said, like, well, maybe it's like because, you know, my autoencoder, like the bottleneck space is too simple-minded. Maybe I should have, say, more than one mode, different modes, like, you know, that describe the structure. You try this Gaussian mixture model, run this, like, you know, in the latent space, nothing works, like, it just doesn't. I mean, this, like, you know, that we're talking here about, like, you know, a year, 2 years of research on that. Every time at the end of the day, the answer is it doesn't work. Now, my former postdoc, Barry Dillon, he came up with an idea that is called the Dirichlet variation autoencoder. So, like, this is a very specific structured space that they construct, and that actually works. And, like, you know, this is where I picked these plots from. So to the right, you see standard ROC curves, receiver operator characteristics curves. So this is signal efficiency of the x-axis, where this background suppression on the y-axis, and upper right is better. And you see that, like, you know, yeah, we get different performance if you either train to the left signal QCD and then you look for tops, or you so to the left, sorry, to left you train on tops and your signal is QCD. Onto the right you train on QCD and your signal is tops. But both of them work. You know, the tagger has different structures the way it does it, but it works in both directions. So that gave us some hope. And then when you look into the latent space, you see that the latent space really just, like, you know, the latent space coordinate where, like, you know, tops and QCD jets are put into to the left and to the right. To the left, these four images, as a function of the epochs, you know, they separate. So you can the latent space does tell you something about, like, you know, what's happening there. From there, actually, we try to do density estimation. Doesn't work. Again, like, you know what, it's a little bit of a depressing history. But then we found, our collaborator here, Peter Sørensen, he found a paper written by, like, a Korean group, and including a Korean graduate student, Sang-Moon, and they proposed a new kind of autoencoder, and it's different in the sense that it tries to not just, like, you know, penalize the too much information, like, you know, like the regular autoencoder, but also the absence of information. And how do you do this? Like, you know, Ramon can you maybe tell you more about this, but, like, you know, the way you do this is you replace your standard MSE training by a so-called energy-based model. So what you do is you construct yourself an MSE, which I call the energy here, but it's really just the MSE. And then you construct yourself as a function of this MSE, as a monotonous function, you construct yourself a normalized probability measure, which is just a Boltzmann mapping. And that has two terms. the numerator. The numerator is just like, rephrasing the MSE just as a monotonous function, as an exponential. But then it has a denominator. The denominator is by definition the integral over all possible solutions, and that you have to calculate. And it turns out that if you do that, this Z generates something like a background metric. So let me illustrate this, like, here on the right-hand side with these two figures. So this is just like, our latent space. It's just like, a sphere that we use here, and we train the network on QCD jets, which are the QCG, which are the blue points, and then we want to see if the tops are different. And you see in the upper image, this is like what an autoencoder does. It separates them a little bit, right? I mean, somewhere in the latent space, you have, in that case, the upper, you have the QCD background in blue. And then when you go further down in this variable, like, one of the directions, lambda, then you find more tops. So like they're kind of separated, but they're not super well separated. And now you retrain your network using this new, Z factor, a second factor, and you see that the background color, the background MSE for these, for that data space actually develops a kind of a mountain on the south side of your map, so that it pushes stuff. And what it does, it pushes QCD really hard to up, and the tops not quite as hard. So it actually compresses the QCD, the QCD landscape, and it get a better performance. And this is, to the best of my knowledge, the best working autoencoder that exists. And what you see here is the MSE. So like, that just like, the reconstruction quality for QCD tagging, which means we train on top jets. Remember, that was the hard part. Everybody can find tops in QCD sample, but like it's hard to find QCD in top sample. And now we have two curves. You have the MSE curve for the tops that we trained on, which is the orange curve, and it has a relatively low MSE, tails in all directions, all fine. Like that's the way it should look. And now you look for the MSE when you feed it QCD jets, right? And yes, they're harder to reconstruct, so they're to the right. They come with larger MSE, right? And they're strongly peaked. And so that means, there are structures which our autoencoder, normalized autoencoder, actually penalizes, or in that sense, the absence of structures, it penalizes for QCD. You also see this little secondary peak here, because like any structure, I mean, you don't get around data properties. And one of the properties of data is, in a QCD sample, there's always going to be some QCD jets that look just like top jets, and they look like top jets, and there's nothing you can do about it, because they really just like every observer you plot, because it looks like a top jet, and then you have them, and like, no magic can set an autoencoder cannot do magic, and so like they end up in the top sample. So like that's kind of data. The way data works at the LHC, right? So everything is super stochastic. There's no like, clearly separate boundaries. Everything is quantum, everything is noisy, which means, the probability distributions will overlap. But what I want to say here, like, the kind of auto to trigger LHC data, I think. For that, you need to make it, put it on a chip. But you can also use this for like standard, like, data quality analysis. Like, you look at a bunch of jets, and, there's two reasons that you might want to look at jets. Like, one is you want to look for new physics, like if you're ambitious. And then there's also the more conservative people who say, I just want to understand if my detector worked, but then exactly comes out the same question: do my jets look like they should? And like, I know, for instance, CMS is using these autoencoders for like, just quality tracking of their data. So that's a very, very big step. And the reason why I chose this example, by the way, is that this is an analysis method that without machine learning we wouldn't have. Like, normally searches, I don't know if you could write them down without machine learning, but nobody has at the LHC, right? So that's new. That's like, that's a new thing that we're going to do at the LHC, and like people are looking into it, and it's great fun. So I also try to, like, the usual story, you try many things and you fail a few times, and then at the end of the day, you find something that works. That's always the same story. There's one thing I also want to say here is like, because it's also kind of like typical for what we do in our group in Heidelberg and other machine learning groups do as well, is, you know, you have to watch the machine learning experts. Like, most of them I might not care about, but there are those ideas, those papers, those tool development, like conceptual ideas that I want to take, and I want to play with them for the LHC, and they're going to make a difference. Right? I don't have to discover everything myself. Nobody has to discover everything themselves. And machine learning, you know, there's a huge field working, like, you know, on, like, you know, common progress, and I think particle physics should, like, you know, just join them and like benefit from them, and also, like, you know, give things back, like uncertainties. Okay, the next thing I want to talk briefly about is generative networks. I know Armand will talk about that with you, or did already, or will. So the question is, essentially, generative networks are like hot because you can generate new images, text blocks, whatever, like, you know, all in all our everyday life. Like, you know, we know the internet is texts are by now, the internet texts are by now generated super efficiently by, like, you know, text bots. Images, like, you know, to train car cameras, there are companies who don't do nothing but generate images, etc. So if you look at them, what are they doing is they encode density in target space, or phase space in our case, and then sample from, for instance, a Gaussian into that space, and then you generate new stuff, right? By the way, like the first generative network for LHC was, like, you know, the Calogan network in, I don't know, 2017, something like that, 18. So, like, you know, it was on calorimeter, and then, like, you know, also later on events. And so the idea is that you produce training data, but statistically independently. So you produce an independent set of, like, events which has exactly the same physics information that your training data has, right? Something that I like and we're working on, and I know you heard about Bayesian networks, and Bayesian networks are my favorite networks. And, like, you know, what we did for the first time is actually extend that Bayesian network concept to generative networks. So you can do the same thing, which means you can encode, like, not just like a density, but also the uncertainty on the estimated phase-space density in a network. So you know how well you have learned stuff. And you'll see, so all my plots, when I show stuff, like, you know, in the generative networks results, they always come with an error bar. This is a Bayesian network error bar. So now there is at least four different, like, you know, standard architectures for generative networks, which are variational autoencoders, GANs, normalizing flows / diffusion models. So normalizing flows as, like, you know, if you want, like, you know, a natural extension of them is so-called more modern diffusion models, and you're going to hear about them. And then generative transformers, so generative pre-trained transformers, so GPTs. And all of them have different strengths and weaknesses, and you just, like, you know, when you have a task, depending on the level of precision you want, depending on your dimensionality of your phase space, depending on, like, you know, the size of your structures, you just pick your favorite model. You know, I'm a big fan of normalizing flows, for instance. Our Heidelberg version is called INN, but I'm going to show you something different. I'm going to show you some work we recently did on GPT. And we call it JetGPT, our tool. So let me just briefly explain how such a transformer works, because transformers, like, you know, are the great magic of machine learning these days, and they're really simple. So what they do is they encode correlations through a so-called self-attention. So if you think of data as bins in phase-space directions, you look phase-space directions, you look at bins, then what you want to understand is what's the relation between the correlation between those kinds of bins. If you do language, like, think of this as a sentence, different words, and you want to understand, like, you know, which words in a sentence actually are, like, tied closest to each other. For instance, an adjective is, like, you know, is very closely tied to a given noun. A noun is, like, you know, tied to the verb. Like, you know, the adjective and the verb are much less tied, right? So, and then you understand language, or you understand LHC events. So now think you have an input X, and you need the link between XI and XG. Think of it as a matrix, right? So how do you construct that? Well, what the network does is it constructs a representation of your point X that you start with, and we call that vector Q. And then it constructs, and that's just a matrix rotation. And it also constructs for all other axes, it constructs another representation, and then we call that K. And then it defines the relation between your point, original point, and all the others as a scalar product in this Latin space. Now that is simple. I mean, this is really just like, linear algebra 1. I mean, 1. It's just a scalar product of two latent representations. And then it, what it does, it normalizes these A's, these A's, and and it makes them so they sum to 1, and they're smaller than 1. This is a softmax step. And then all it does, it takes to evaluate something, another point. It takes yet another matrix, constructs a representation V, and then on the bottom right, you see it analyzes V in the space of A. A are the projections, this is the rotation angles that you constructed between Q and K. And in that space, you analyze X that you can first call V, analyze it in that space, and you give it all as Z. So which means it's just a big basis rotation. I mean, it's an automatic learned basis rotation. So you have an appropriate latent basis with a lot of degrees of freedom, and you just learn that. And the idea is that this self-attention then gives you a representation. Think of it as a matrix that knows from the data how closely tied two entries are. Think of it a matrix. And if that is they're closely tied, then this is a large value. And if it's less correlated, it's a small value. Right? And that's really what they do. So this is what a transformer does. It works in this space. Now you see that this is learning all correlation. That is immediately clear why transformers take forever to train, because you need to learn all of that structure. You could also argue that as physicists we often know what the structure is, but whatever, we can do that. The second thing that the transformer as a generative model does is autoregressive. So it assumes that your phase-space density is a product of conditional densities going from one space dimensionality to the other. So if you first evaluate, say, the angular correlations, some angle, and then given that angle, you now walk into the next direction, which could be the rapidity, and then you walk another direction, which could be the PT. And the key is that you do one of them after the other. Right. So you have some stuff that you understand really well and that you put early, and the stuff but everything just looks the same, where the network has just to learn that PT is just a power law that you put to the end, because this is the same everywhere and there's no structure in that. So this is a benefit, the potential benefit of these transformers. Yeah. So technically the thing that we do is for LHC events, we place our bins by Gaussian mixtures in phase space. Okay, that makes them fewer, right? And then strictly speaking, because we do this factorized density, you can only dimensionalities, information can only go one direction. You actually make the assumption that you first evaluate, as I said, the angle, and only then you evaluate the rapidity, which means the correlation can only go in one direction. So your A matrix that you use becomes 0 in one half, and then encodes the correlations only in one direction. And that's it. That's it. That's ChatGPT or JetGPT for you. But this is what these networks do. They learn all correlations, and then they they sample from them in a conditional setup. Our playground for that is Z plus jets production. So that we basically look at Z plus 1 to 3 jets, and let me show you some numbers, right, from a paper we recently wrote. So because of this, the autoregressive setup, these tools have a relatively easy time understanding different numbers of final state particles, because you do this autoregressive conditional thing, and but it ends when it ends, right? If there's more particles, it ends later. But you can just and if you have fewer particles, it ends because you have no particles left that you want to construct. So this kind of conditioning in principle is relatively structurally easy to implement. And here you see, for instance, the PT spectrum of the second hardest jet. You see you produce stuff with nice precision. You, by the way, see now the blue arrow in the second panel. The blue arrow bar is from my Bayesian networks, and they agree with truth, like, the one line within these uncertainties, an important check. The arrow bar gets bigger to the right with less training data. Ask him, he's done all of these things many times. What's nice here is now you do this for Z plus jets, so 1, 2, 3 jets, and you look for the sum, the scalar sum of those PTs. This is like something that that's jet inclusive, and you see it can do that as well. Yeah, so like, here for these, like, networks, it's very easy to describe like a variable number of final state particles, which in many networks is a pain to do, but for those it's easy. But then nothing comes for free. So for, if you now try to understand, like, try to like see how well the network has learned the Z mass or the invariant mass of the muons, you see that the 10-15%. So our net like, you see that, like, it just mismodels the Z peak, not dramatically, but certainly not the way we like this from LHC physics. So this is, we can't do that. Like, that's not so good news. On the other hand, some of the correlations here, you see the delta R between jet 1 and jet 3 is actually modeled quite nicely. I mean, there's a slight deviation at the very, very end of to the left. But that's like within, like, the expected performance. So that's an example where, like, you have a new network. It is convincing. It does cool stuff. It does some things nicely, like, delta R. It fails on the Z mass peak, which means more work to do. This is why we're not yet employing that. So, like, these new networks, they come up, like, of course we're interested. Like, everybody talks about JetGPT, and of course we're like, you want to try them out on LHC events. So, yeah, so we did, and that's the answer. And we're not ready for like what we call production runs. The last thing, I want to talk about, the last example is something that, like, as a theorist is important, is close to my heart. And it's basically how to learn formulas. So imagine something that's complicated, some complicated structure in data. So that's, for instance, if you look at the likelihood, the so-called score or an optimal observable. So, like, you want to know what kind of observable produce the best possible results on a given, like, new physics effect. And so if we write down the single event likelihood as P of X given a parameter theta, which is the one parameter we want to measure, we can take the likelihood ratio, which is according to Niemann-Pearson. Niemann-Pearson lemma is like the optimal observer, the best discriminator for that, and like an estimator for that. And we can just we can Taylor expand it. And the dependence on theta here on the right-hand side on theta is called the score in data science, or the optimal observable in particle physics. And in particle, we can write down in particle physics, if you can write down the probability as a matrix element standard model squared plus an interference term with a new physics parameter linearized, I can actually calculate T, and T is just a matrix element interference term divided by the standard model squared. At pattern level, at leading order. Problem is, the world in experimental science is not pattern level and it's not leading order. So, like, can I do better? Can I learn this structure? You see, this is something that depends on on these likelihoods, which means you should be able to extract it numerically, and we can. The example I'm going to give you is the CP violation through dimension 6. Because it's a very well-known search that Atlas and CMS are doing, and we know that we can test CP violation in weak boson in the Higgs sector using weak boson fusion. And the best observable to look at, that goes back to Dieter Zeppenfeld, is the sign of the azimuthal angle difference of the two tagging jets. That's like, that's the optimal observable for that. The only problem with that is that we don't know. I mean, Dieter does, but like, in addition to this delta phi, what's the right prefactor? The right prefactor comes from the fact that you have dimension 6 operators. Dimension 6 operators come with a modified momentum dependence. So, like, there's also like, a prefactor which then you calculate, and it's called PT of the tagging jet 1 times PT of the tagging jet 2. So, like, you have to construct this observable as the optimal observable for the CP violation in through a given dimension 6 operator. So that's our task. I can simulate that. I can simulate these events. I can calculate these cross sections. I can do pattern shower on them. I can do detector simulations on them. And then I want to know what is the optimal observable after detector. So what you do for that is a tool called symbolic regression, and specifically PISR by Miles Cranmer, plus some modifications that we included. And what it does is it takes a function model observable, and I know what my parameters should be, like my phase space, parameters that should appear there. I want to express this in PT or delta eta or delta phi, right? And I also know how I want to relate those two parameters to two of those parameters. Like for instance, I want to do the sine of delta phi. I can guess this ahead of time. I want to square something. I want to multiply things. I want to divide things, right? So now the trick behind symbolic regression is that you represent your formula as a tree where you link parameters through operators, and you can write this down as a tree function. And then you construct these trees, and you construct these trees by writing down a tree, evaluating the function according to your tree, and then comparing it to simulated data, my function t, but that comes from some Monte Carlo code, right? I don't know what the formula is that was used to generate it, but probably something complicated. And you calculate the MSE, just the agreement between these, between your language and your data. Now, that's standard, brings us back to my first slides, right? MSE, just to compare. And and then you minimize the MSE, and you minimize the MSE under the boundary condition that you want a certain maximum complexity, a certain number of parameters and operations between them. And here's what for a complexity of 3, which means 3 objects, parameters and operators combined, you get 8 a function times delta phi. So phi1 minus phi2. And you get a certain MSE, which is on the right-hand side is shown, and then you go to higher complexity, and the function that the formula that PISR learns becomes more and more complex. By the time you look at first it does it as a sine delta phi, and then it makes a sine of delta phi, and then it adds xp, x is just pt, and then it combines a sine and x. And then it adds another finite shift constant, and so on and so forth. And every time it does that, the function agreement becomes better. The MSE goes down until you hit complexity 16. Complexity 16 is the final formula, because if you allow for more complexity, you're not getting any better. And formula 16 is interesting because it's after detector effects. And we know already what the formula is. It shouldn't be for formula 16, right? It should be more something like 8, pt1 times pt2 times sine delta phi. However, that detector effects do appear, for instance, on eta, depend on eta. So 16 now has a dependence on eta, something that at the pattern level doesn't exist. But if you take it into account detector effects, it does exist. And you can basically, this is just the expected p-value from analysis, and you start with a very wrong formula, which is just pt1, pt2, has nothing to do with CP violation. And you see that your expected limit on your f Wilson coefficient is horrible. And then you make the function better, a sine of delta phi without any pt dependence. It gets better, right? It tests something, but it's not as good as the Matt Minor results from Karl Kramer and collaborators, which are in the screen curve. But then our symbolic regression result that I just showed you, figure that's here. That's even only 8. That's number 8. You see, it's numerically totally identical to the within uncertainties now to the full result. So I can calculate these optimal observables, but maybe I can. Maybe it's too hard, in which case I can look at the data, and instead of calling a very, very complex numerical function, I can write a one-line formula. And that one-line formula I can put in, it reproduces the performance, and it also can be interpreted immediately, right? I can check, for instance, is there a big eta dependence, which means is my optimal observable also strongly affected by detector effects or not? And that's nice because, as I said, the language of physics is not Monte Carlo code, but it's formulas. at the end of the day. Something that, by the way, Miles Kramer always emphasizes. He's a cosmologist. Same thing, not just particle physics. Okay, and with that, I'm done. Let me just summarize machine learning applications for LHC theory, LHC physics. If you want, just think of them as just another numerical tool for a very numerical field, driven by funds that we don't have to pay for because, data science, medical research, everybody pays for it, and we can just use stuff. And that's a great opportunity. What we want at the LHC is we want to improve established tasks, do stuff better that we already know how to do. But it gets more fun if we can develop new ideas, run autoencoders, anomaly searches at the LHC for a trigger, or the kind of unfolding that Ramon will tell you about. That's actually somewhere between category 2 or 3. It's something that maybe we thought about before, but nobody ever thought that you could actually pull this off in reality. What I like as a physicist is what people nowadays call explainable AI, because it's all about visualization. And explainable AI for a physicist is something very different. Explainable AI for a physicist means I want the error bars. Main thing explainable, give me the error bar. Uncertainties generally systematic statistical uncertainties, just the precision, symmetries, formulas. That's the way I think of physics as explainable AI. And that's why it's so much fun to do this as a particle theorist. And then, you can have lots of new fun with old LHC problems, right? I mean, in the old days, LHC physics was mostly hard, difficult, certainly worthwhile, but very hard work. And I think using machine learning for these kind of things is gives it a new flavor of fun and lightness. And so, enjoy the opportunity for the young generation. I should also advertise, we have a set of lecture notes where we wrote up lots of things that on Heidelberg that we either thought was super cool or that did. But again, Ramon can tell you more about this. Thank you so much.